Professor John Thuburn is participating from Exeter in the UK. So let me tell you a little bit about John. He did his undergraduate studies at Cambridge in mathematics and his Doctor of Philosophy at Oxford in Middle Atmosphere Dynamics. And he spent 16 years in various positions at the University of Reading. And then in 2005, he took up the chair in geophysical fluid dynamics at Exeter. And that chair is jointly funded by the Met Office, with which he's worked very closely over the years. He's, in my opinion, the leading numericist working in our field today. And he's been instrumental in the development of Endgame, Gung Ho, and Paracon. I'm not sure how much he had to do with those names, but these are important projects in the UK and on the operational side as well. So John, thank you for doing this. I really appreciate it, and I turn it over to you.
Thank you very much, David. That's very flattering remarks. Can you all hear me and see my slides?
Yeah. Yes. Yes.
Super. Thank you. Well, it's a great honor to be invited to be a keynote speaker at this symposium in honor of Professor Arakawa. I'm really sorry that I can't be there in person to join in the wider discussions and reminiscences. I thought I might take this opportunity to talk a bit about a couple of strands of my own research in numerical methods that clearly lead back to Arakawa's work and builds on Arakawa's work. So touching on geostrophic adjustment and conservation. It's also an excuse to use this terrible pun about hidden jewels. We'll see what that refers to shortly. Okay. So a brief outline. I'll talk a little bit about geostrophic adjustment, of course, building on the Arakawa ABCDE grids, how we might extend those ideas to other grid topologies, such as hexagonal grids and even unstructured grids. Then I'll switch tack a little bit, although the two threads are interlinked, and talk a little about energy and potential entropy conserving schemes, and mention a finite difference, finite volume type approach, and then more recent ideas based on compatible finite elements. And if I leave enough time, I'll briefly mention at the end an issue that arose in vertical discretization, but has some links to the horizontal discretization issues I will talk about in the first part of the talk. Okay, so let's kick off with geostrophic adjustment. So Arakawa and Lam, building in 77 paper, building on the work of Winninghoff's thesis, they noted the importance of properly simulating geostrophic adjustment.
I've lost the audio. Let's hopefully you can hear me. So let's wait until it's fixed, and I'll give you a signal.
Okay, can you still hear me?
Yeah.
Oh, okay, good. So I'm not sure how much you missed. This is all well-known stuff. Arakawa and Lam, building on Winninghoff's thesis, emphasized the proper simulation of geostrophic adjustment. Okay, so we know that the energy-containing motions of the atmosphere are the slow, geostrophically balanced and hydrostatically balanced motions. But there are many processes continually disturbing the atmosphere away from that balance, and it's important to capture that adjustment. The processes, the radiation and dissipation of fast waves by which the atmosphere adjusts back to that balanced state, sort of continuous process. And so famously, Arakawa and Lam and Winninghoff noted that a proper simulation of geostrophic adjustment depended sensitively on how one placed the variables on the model grid. Well, I'm sure everyone in the audience knows about the A, B, C, D, and E grids, and then Dave Randall later added the Z grid or Z grid. And one can, on these nice square grids, one can systematically analyze how a numerical method captures or fails to capture the geostrophic adjustment process. Basically, what one does is write down the linearized shallow water equations, look at the inertia gravity wave dispersion relation for the continuous equations and their discrete analogues, and see how well they compare. And usually what happens is that a scheme behaves badly if some of the important terms are averaged. So on the B grid, it's the pressure gradients and the contributions to the divergence that are averaged. So the overbar with an X or Y indicates an average. That means the B grid works well when the Rossby radius is unresolved and it's the Coriolis term that's dominant. In contrast, on the C grid, it's the Coriolis terms that are averaged. C grid works well when the Rossby radius is resolved. So that's all well known. And then Dave Randall pointed out that the Z grid gives you the best of both worlds, provided you're prepared to pay the price of solving an elliptic problem to get the velocities back from the vorticity and divergence. Actually, this is a remark that Arakawa made in several different contexts, but it applies here as well. He noted that going to higher order doesn't necessarily help you, and that's true in this case. Going to, say, fourth order or sixth order doesn't avoid the fact that these terms are averaged. The averaging comes from the placement of the variables on the grid. Higher order doesn't avoid that averaging. Okay, so one might let's put back to the C. So on the C grid, the Coriolis terms are heavily averaged. So one might suspect that the slow balanced motions, the Rossby waves that depend on the Coriolis term, might not be well captured. And indeed, that's what previous theory had suggested. So there is several papers in the literature, mostly based on quasi-geostrophic theory, that predict poor, inaccurate wave propagation for the marginally resolved Rossby waves on the C grid. On the other hand, some work that I'd done with Andrew Staniforth, computing numerical normal modes, suggested that actually the C grid works quite well, thank you very much. So what's going on there? Well, what we'd like to do is include the beta effect in the kind of analysis that Arakawa did in order to look at the Rossby wave propagation as well. Well, if we simply make f, the Coriolis parameter f, vary linearly in latitude, that's an obvious way to include the beta effect. Unfortunately, our governing equations no longer have constant coefficients, so we don't have solutions proportional to e to the I kx plus ly minus omega t. So we don't have nice wave-like solutions, which we'd like to keep the analysis tractable. One thing we might try is to take the curl and the divergence of the U and V equations to form vorticity and divergence equations. So zeta here is the vorticity, delta is the divergence. Having done that, so now that we've made f and beta appear, we could think about freezing the coefficients f and beta, making those constants, then we would have constant coefficient equations. The trouble with that is these equations no longer conserve energy. So we do have wave-like solutions, but the system's no longer stable. The little trick that we need, which I think goes back to Andy White and Roger Grimshaw in a different context, is to replace beta v by beta times the rotational v and beta u by beta times the divergent u. That restores energy conservation and gives us nice stable solutions in a system with constant coefficients. And if we like, having substituted wave-like solutions in these equations, we can undo the div and the curl to recover the momentum equations. And they look almost like they did before, except instead of the frequency omega, we've now got an omega tilde, where omega tilde includes a contribution from the beta effect. So capital K squared is the total wave number squared here. And the dispersion relation is at the bottom of the screen. So it's now got a couple of omega tildes instead of omegas. But otherwise, it looks very like the usual shallow water F-plane dispersion relation. Okay, so now we can pick up the beta effect and get Rossby wave solutions out of at least the continuous equations, as well as the inertia gravity waves. So now what we'd like to do is repeat all of that, all of those steps for the discrete system. And you generate quite a lot of algebra. I meant to say I'm going to try to avoid a lot of the gory mathematical details in this course, but in this talk, but I've slipped in little references here in the magenta color. It's a list of references at the end if anyone wants to follow up the gory details of the maths. Okay, so now we can do the analysis with the discrete system. And as I say, I'll spare you the pages of algebra and just point you to the key term, which is, or the key terms, which are the Coriolis terms. So in the previous work, they'd looked at the heavily averaged Coriolis terms. Now we have some options for what we do with the Coriolis parameter f, but the simplest thing, since it's easy to do, is just to evaluate f wherever it's needed. That's what the previous work did. If we look at the divergence of the Coriolis terms, which appear in the vorticity equation, then we get an f times an average divergence, and we get a beta times a heavily averaged v. So this is a 3 times averaged v. And this heavy averaging of v leads to a drastic slowing of the Rossby wave frequencies. So let me talk you through this figure. I've fixed the zonal wave number and looked at different latitudinal wave numbers on a grid, and this is the wave number limit is the last point on the graph. The diamonds are the solutions of the equation on the previous page, so they are the exact frequencies. The crosses are the solutions of the frequencies for the discrete system. The top curve is the inertia gravity waves, so we're doing a pretty good job on those. But the bottom branch is the westward propagating Rossby waves, and you can see the numerical Rossby waves are severely slowed. So let's contrast that with what Andrew Staniforth and I found. So it just so happened that we'd been looking at Arakawa-Lamb type energy conserving schemes, and so we discretized the FU term in a slightly different way. We'd multiplied F times U, then averaged. And that makes a crucial difference. So now when we take the divergence of the Coriolis terms, we get, again, an F times the divergence average. Note this is a slightly different form to what we had before. But now the beta term pops out with just a single average, a single zonal average on the V term. There's no meridional averaging. And now the Rossby waves, we do a much better job. Okay, so a couple of points to make about this result. First of all, it turns out energy conservation is a bit of a red herring. It was just a coincidence that we were looking at an energy conserving scheme. But if we look at other members of the family that Arakawa and Lamb derived, there are other energy conserving schemes in the family, we can get different kinds of behavior, including eastward propagating Rossby modes, which is clearly the wrong sign. So energy conservation is a red herring. The other thing I want to point out is that in both of these approaches, we get some kind of averaged divergence term appearing in the vorticity equation. It's a slightly different form in the two cases, but there's some kind of average divergence. And that's an idea that will pop up again and again in this talk. Okay, so I was feeling quite pleased with myself having got this result, and I wondered if one might be able to apply the same trick for including the beta effect on other grids, like hexagonal grids. I was just starting to get interested in quasi-uniform grids on the sphere at this point. I'm slightly embarrassed to say that at that point in time, I'd forgotten all about the Nikovich et al. Result. So what Nikovich and colleagues had done was try to repeat the Arakawa-Lamb Winninghoff analysis, but on hexagonal versions of the A, B, C, D, and E grids. And they'd found a rather unencouraging result for the C grid. So the inertia gravity waves behave quite nicely, but the geostrophic modes, which should have zero frequency, they should just sit there and be steady, actually weren't steady. So what the diagram on the right shows is, so the axes are dimensionless wave number in the zonal and meridional direction. D is a measure of the grid cell size. And the contours are contours of wave frequency. Of course, that frequency should be zero. This plot should be blank. but actually the frequencies are getting up to, I should say, the frequency normalized by F. So the frequencies for the smallest resolved waves, which are in the corners of the hexagon in wave number space, getting up to about a half of F. So they're not even small frequencies, they're large frequencies. That means the hexagonal C grid can't sustain a geostrophically balanced flow. That's very, very discouraging for the hexagonal C grid. The devil's in the detail. So the challenge on any type of C grid is how do we construct the tangential velocity components? So we're predicting the normal velocity components at every cell edge. The challenge is to construct the tangential velocity component that appears in the Coriolis term. And Nikovich et al. Did the obvious thing, which is to take the 4 nearest neighbors and work out what weightings they needed to construct the tangential component. Okay, so of course, as soon as I tried to analyze this case, I was very quickly reminded of the Nikovich et al. Result. But because I was focusing on the C grid, I persevered a bit, found myself drawing diagrams like the one on the right and thinking about the vorticity budget. Now, on any shape of C grid, the vorticity lives at the vertices. You could think of normal velocity components along these triangular edges, and you could think about calculating the circulation along that triangular boundary and relating that to the vorticity inside the cell. And it's clear once you start drawing that sort of diagram, well, the line of thought that you need to think about. So in order to have steady geostrophic modes, we require the vorticity to be steady whenever the divergence is 0. And one way to ensure that is to make sure that the divergence seen by the vorticity in this triangular dual cell is some sort of average of the divergence in the surrounding cells. And once that penny drops, you realize that these tangential velocity components, I hope you can see that they're red, the Coriolis terms, in other words, must somehow be related to the normal velocity components around the perimeter of this little 3-cell grouping. So that tells you which velocities must come into play. And once you realize that, you see that the tangential velocity at any given edge has to be built from not just the 4 nearest neighbors, but some further away edges as well. In fact, on the regular hexagonal grid, the weighting is 2/3 to 1/3, the near neighbors to the more distant neighbors. And in general, there could be contributions from these other edges as well, but because of the symmetry of the regular hexagonal grid, the coefficients are 0. Okay, so once you make this construction, then the geostrophic modes become steady and life is good again. The hexagonal C grid is saved. Okay, so just to summarize that, so now we've got steady geostrophic modes on an F plane. The inertia gravity waves, they are just fine. With this slightly modified construction of the Coriolis terms, the inertia gravity wave dispersion relation looks very similar to what Nikovich et al. Found. And if anything, it's a little bit more isotropic than on a square grid. We can now go through the motions of putting the beta effect back in. And I want to try and cut a long story short here. So just like on the square grid, there's devil in the detail. It depends a little bit on exactly how we discretize those Coriolis terms. Also, because on a hexagonal grid, we have twice as many vertices as we have cells, we have, in a sense, twice as many degrees of freedom in the vorticity, we get double the number of Rossby waves. We get 2 branches. And the primary branch more or less behaves as it should. The second branch comprises modes that all have extremely low frequency. It's still proportional to beta, but it's very small. And we could have a good debate about whether you want to call these computational modes and whether they're damaging or whether they're neutral or whether they actually add a little bit of extra resolution to your vorticity field. As I say, one can have a good debate about that. Right, let's okay. So I was very pleased with that result as well. Shortly after that paper came out, Bill Skammerock got in touch. It turned out he and Joe Klemp had been working on the same problem. What do you do about the geostrophic modes on the hexagonal C grid? and they had indeed come to the same solution, the same construction of the Coriolis term. The key question then was, can that trick be adapted to slightly distorted hexagons and the occasional pentagon that arises on a Voronoi tessellation of the sphere? Well, in other words, the problem that we need to solve to do global modeling on a hexagonal or polygonal sea grid. And at the time, neither of us knew the answer, but we set to work and got a collaboration going along with Todd Ringler, and it didn't take too long to figure out that essentially the same idea is what we need. So again, we've got to make sure that when the divergence is zero in the surrounding primal cells, we get zero divergence appearing in the vorticity equation associated with the vertex. Now, it's a little bit trickier to figure out exactly how to construct the Coriolis terms in that case, but there's essentially one way to do it that works. And you can sort of reverse engineer it with, again, a bit of fun mathematics. So basically what we want to end up with is, if we start with a velocity field represented by the u's, so the normal velocity component in blue, when we take its divergence and then average to the dual cells, we get the same answer as if we construct the Coriolis terms and then take the divergence directly on the dual cells. So we get this nice little commuting diagram that has to hold in order to get steady geostrophic modes. And we managed to figure out how to do that. And so we can get steady geostrophic modes on unstructured Voronoi sea grids, not just regular hexagons. Okay. So again, that was what else I want to say. Okay, we'll return to that thread of discussion in just a little while, but let's switch tracks just for a moment and talk about energy and potential entropy conservation. So again, I'm sure everyone knows the story of the Arakawa Jacobian. His motivation at the time was to try and control the nonlinear computational instability that Norm Phillips had pointed out. So Arakawa noted that if we conserved either energy or potential entropy, that would prevent the model from blowing up. So in some sense, inhibit the instability. But he argued for actually conserving both, because that then constrains the energy cascade and the spectral energy distribution as well, which was a beneficial thing. Now, I think it's true to say that these days we're much less concerned about nonlinear computational instability. We have nice advection schemes and we have a lot more resolution to play with, so we play a bit more with our dissipation. So you don't see a lot of papers published these days worrying about nonlinear computational instability. A good argument can still be made for wanting to do a better job of energy conservation. So many authors have pointed out this, and I refer to a recent nice review by Peter Laritzin and colleagues. Typical dynamical cores at climate resolutions still have energy errors of order of watt per square meter. And that's a bit too big for comfort still. We'd rather it was a bit smaller than that. Okay, but I think there's still a good case for wanting energy conservation. Okay, and again, this story is well known, but I'll just recap briefly. So Arakawa and Lamb, 77. So Arakawa had already decided that the sea grid was the way to go, but they were working with the momentum advection form of the equations. And again, this is a recurring theme. They've carefully gone through the derivation of energy conservation for the continuous equations and then tried to mimic key steps in that derivation in their discrete, in their discretization. So, to try and capture key identities and key cancellations to make sure that the discretization was energy conservation. And the key step was to formulate the momentum advection so as to try to mimic how the Arakawa Jacobian worked. And they managed to do that in the case of non-divergent flow. Interesting is, a little aside, they made use of you might call it a dual mass equation or an auxiliary mass equation that lived at U and V points on their grid. By 81, Arakawa had become dissatisfied with the earlier scheme because it didn't work so well in the presence of steep topography. They wanted, or they argued that, they wanted better control of the potential vorticity, which meant they would like to have, for example, potential entropy conservation for arbitrary flows, not just non-divergent flow. And so they switched to using the so-called vector invariant form of the momentum equation. Again, they want the finite difference scheme to mimic various identities and cancellations. And this time they used a dual mass equation that lived at vorticity points. Okay, so that's a little bit of background. And so various other authors had developed schemes inspired by Arakawa and Lamb on other grid structures as well, such as the Voronoi tessellation. So what I think it was actually Todd Ringler who noticed that the construction I described earlier for obtaining steady geostrophic modes on unstructured grids actually gave us a lot more than that. So he realized that if we apply our little commuting diagram to the mass flux rather than just the velocity divergence, then we get a dual mass budget living on the dual cells. And then we can exploit that to obtain either energy conservation or entropy conservation, or potential entropy conservation by using, so here I've written down the so-called vector invariant momentum equation for the shallow water case. So let me particularly point out the Coriolis term here. So you take the mass flux, rotate it through 90 degrees, multiply by a reconstruction of the potential vorticity at the relevant edge. And depending on what you do with that term, you can obtain different properties. So you can construct this term so as to obtain energy conservation. You could construct it so as to obtain potential entropy conservation. It's actually not easy to use to obtain both at the same time, because we've used up a lot of our wiggle room, our degrees of freedom to obtain the steady geostrophic modes. Yet another thing one can do is note that when you take the curl of the momentum equation and combine with the mass equation, you obtain the potential vorticity equation. And the flux in the potential vorticity equation is exactly this term, this F per Q. So one thing you can do is take your favorite advection scheme for potential vorticity, work out what the fluxes are, and plug those into the momentum equation. And then your potential vorticity will evolve exactly as if you had advected it with your favorite scheme, even though you're actually predicting the momenta. So that's actually the approach I tended to use in my later work. But at the time, we actually tried both energy and potential entropy conservation. Okay, and this approach later became the basis for the MPAS dynamical core and GCM. Okay, let me backtrack a moment. Right, so in all of this work up to this point, we're working on Voronoi tessellations, which means these dual edges are perpendicular to the primal edges. And we were exploiting that property in constructing these schemes. But it turns out with a little bit of extra mathematical machinery, you can get things to work on a non-orthogonal grid as well. So something like a cubed sphere grid, one can, I don't know if this diagram's big enough, you can construct a dual grid on a cubed sphere as well, but the dual edges are no longer orthogonal to the primal edges. But with a little extra machinery, you can make things work as long as you smooth the grid in just the right way. So we actually, we're now getting into the early days of the Gung Ho project, which is developing the next generation die core for the metaverse model. So we constructed a shallow water model based on these ideas that could work on either a hexagonal grid or a cubed sphere grid, and tried it out. It worked reasonably well. But one thing that bothered us was that although we've got this nice steady geostrophic mode property, there's a bit of a price to pay, which is that there's a numerical inconsistency, if you want to be harsh about it, in the calculation of the Coriolis terms. So if you set up a nice smooth velocity field, like a solid body rotation, and do a systematic convergence test you find the maximum errors in the Coriolis terms just don't converge to zero. They do occur over smaller and smaller areas, but they don't converge to zero. So that was a bit discouraging for this approach. Now, how big a problem it is for simulating the weather and climate, again, we could have a good debate about this. So when you do a test case of reasonable complexity, like the Williamson et al. Test case 5, that's the, you start with a solid body zonal flow, and you stick a conical mountain in mid-latitudes, where the circle is here, that generates a nice complex flow. And okay, so what I've plotted here on the right are the height errors after 15 days, I think, from 3 models. There's 3 shallow water models. One's based on the hexagonal grid, one on the cube sphere grid, and one uses a semi-implicit semi-Lagrangian scheme on a lat-lon grid. And if I didn't tell you which was which, you probably wouldn't guess which was which. And that's the point. The errors are not significantly bigger, despite this inconsistency, than they are on the semi-implicit semi-Lagrangian grid. So again, one could have a good discussion about how important this sort of issue is. But that was enough to discourage us, since it was early days in the project development. What I want to get to. Yes. Okay, so what we found, I mean, even going all the way back to Arakawa and Lamb, we've found we've been forced to use up our degrees of freedom, if you like, our wiggle room in the design of the scheme, as we've gone to hexagonal grids and then unstructured grids. We've used up more and more of our degrees of freedom, constructing well, what we hope are nice properties, but in a rather ad hoc way. And it does beg the question, are there more systematic ways of getting these nice conservation and steady geostrophic mode and geostrophic adjustment properties? In fact, I love this quote from Rick Salmon. He says the AL algorithm, referring to Arakawa Lam 81, remains a stunning and somewhat mysterious achievement. Yes, I always felt that Arakawa had a little bit more intuition than he was letting on when he wrote it in the papers. How did he come up with those extra terms that one wouldn't normally think of to make everything hang together? Okay, so that begs the question, are there more systematic approaches to obtaining these nice properties? One approach, which I won't say very much about, well, I won't really say anything, but I'll just point it out, approaches based on Hamiltonian ideas, such as Poisson and Nambu brackets. So I think it was Rick Salmon and Lintale who noted that the Arakawa Jacobian could be derived from a certain Poisson bracket. Then there are various other contributors, like Almut Gassman, Marine Todd, Chris Eldred, and numerous others. So this does look like a very interesting way forward. I won't say any more about that today, but the approach we took in the Gung Ho project was one based on so-called compatible finite elements, or mimetic finite elements, if you want to call them that. So what are they all about? So, okay, so I think we're all used to the idea that in the finite element method, we require that our solution live in some sort of function space, built up of simple basis functions. So here's an example of a piecewise constant function on a triangle. If we discretized our domain with triangles and had piecewise constants everywhere, that will be one sort of function space. The idea with compatible finite elements is that we introduce several function spaces related to each other in a very particular way. Give it its technical name, it's called a de Rham complex. So what we require is that, where should we start? Over here. If we take any function in this space at the left, and take its gradient and perp that, rotate through pi by 2, we get a function in the middle space. If we take a function in the middle space, so this these are vectors that live in the middle function space. If we take the divergence of any function there, we get something that lives in the right-hand function space. this is a 2D version of the compatible finite elements. So we have 3 spaces in total. Moreover, if we start with a function in V0, take its grad perp, and then take its div, we get 0. So the grad perp maps onto the kernel of div. Now these operations, the grad perp and the div, are exact pointwise operations. Well, that's, again, I'm doing okay for time. Let's pick the example of this velocity basis function. So we have in this example, we have a constant normal velocity along the middle edge, and then the divergence is uniform on each of the triangles. So if we take a div of that middle element, we end up with something that can be built out of piecewise constants. Okay, so and that's true at any point in space. We can also define gradient and curl operations going back in the other direction, but we have to define those in the usual finite element way, where we multiply by some test function and integrate by parts if necessary. So that's why I've indicated them with dotted lines, or dashed lines rather. They're defined only in the sense of integration by parts, whereas the derivatives heading towards the right are exact pointwise operations. Okay, so the hard work is setting up these function spaces in the first place and convincing yourselves that they have the right properties. But once you've done that, a remarkable cornucopia of benefits accrue. And there's Colin Cotter who pointed this out to us again in the early days of the Gung Ho project. And you can imagine my combination of dismay and delight. Delight because it all works, and dismay it sort of supersedes all my earlier work. So what do we get? So we get, it turns out, the degrees of freedom if we choose, slide it back, if we choose our function spaces as I've sketched them on this slide, then the degrees of freedom are placed exactly as they would be on a C grid. So we have a C grid-like placement of variables, and if we work out the dispersion relation for a scheme based on this approach, it inherits all the benefits of the C grid placement, including the nice geostrophic adjustment. What else? If you specify a vorticity field, you can always find a phi field that will be in balance with it. And in particular, geostrophic modes are steady, and that just comes automatically out of the framework. And in particular, we have, let me backtrack to the previous slide. So it's natural to define velocities and mass fluxes at edges like this, which means when we take the divergence, the divergence will naturally live in this V2 space in the piecewise constants. But one can construct an averaging operator, or well, again, it's an integration by parts using test functions from this space. And so we can map the divergence onto the vorticity space. Equally, we can construct a V perp. Again, we just integration by parts in the usual finite element way, and then take the divergence of that V. Well, we take the curl of the V perp, which effectively gives us a divergence living in this space. So there's 2 routes to constructing a divergence in the vorticity space, and they commute. So just like the property we had in the finite difference finite volume scheme earlier, we get a nice commuting diagram coming out of the compatible finite element approach. What else? We get divergence and gradient being negative adjoints of each other. That essentially just comes from the integration by parts definition of grad. So that comes again straight out of the framework. And also it automatically drops out that if you construct the V perp multiplied by V and integrate, you get 0. So these 2 bullet points together give us energy conservation. And indeed, we can also get potential entropy conservation if we construct the nonlinear PV flux in just the right way. So in other words, once we've set up this de Rham complex, this family of compatible finite elements, all the nice properties that we worked so hard to get previously just come out of the framework automatically. Okay, so that's rather nice, but job's not quite done yet. So the example I used to illustrate things was based on triangular cells. Now the triangular C grid is not without its issues, although the German icon model does use a triangular C grid because it gives them the option to dynamically adapt. But a triangular C grid has if you like, the opposite problem to the hexagonal C grid, in that it has excess degrees of freedom for the height and divergence fields, and therefore has extra branches of inertia gravity waves. And these extra branches do behave badly in certain circumstances. So at least within Gung Ho, we didn't want to use the triangular version of these elements. That's not too bad because there exist quadrilateral versions of these compatible finite elements as well. But their downside is they don't automatically wrap the sphere nicely. You can place 3 corners of a quadrilateral on the sphere, and then you have to bend it to get the 4th one to lie down. Now there are, well, that's not the end of the world for quadrilaterals. You can use something called a Piola transform to bend your elements onto the sphere. But that approach also comes at a price. Also, what about the hexagonal grid? Do we have to abandon hexagonal grids if we're going to use compatible finite elements? Perhaps we can construct hexagonal versions of them. And then finally, around about this time, I was a little bit obsessed with the idea that we'd like our PV to behave, our potential vorticity to behave exactly as if we were advecting it directly, even if we're actually predicting the U and V equations. Which meant that I wanted to use a finite volume scheme for advection of potential vorticity rather than a finite element scheme. So it turns out we can address all of these points by constructing what you might call compound compatible finite elements, which is an idea actually originally suggested by Snorre Christiansen, but I don't think actually implemented anything. He worked out the theory for them for how to construct them, and we actually coded them up and put them into practice. When you do that, you can introduce a second family of these finite elements, if you like, a dual family that lives on the dual grid. So when you do that, you get these wonderful objects. Let me just talk you through the middle row, which is the hexagonal version. So if you want a piecewise constant basis function that lives on hexagons, one way to do that is by gluing triangular piecewise constants together. In this case, it's obvious how you glue them together. In fact, you could do it with fewer than 12, but the reason I've done it with 12 triangular subelements is that I want to be able to compute integrals on the overlap between hexagons and triangles. So when you figure out how many you need, it turns out you need 12 subelements glued together to make one hexagonal element. Likewise, you can build the velocity basis elements out of triangular Ravier-Thomas elements, if you like. So the divergence is constant actually across the whole hexagonal half, and it's the opposite across the other half of the element. And there's a constant normal flux across the middle edge and 0 flux across the outer edges. So that's our basis velocity element. And then in the vorticity space, we have this wonderful crystalline structure that's made up of piecewise linear triangular subelements. And they're all glued together in just the right way, using Christiansen's idea of discrete harmonic extension, if you want to get into the technical stuff. Again, I'll skip the gory maths, but it's all doable. You can do the same thing on quadrilaterals and on triangles. And of course, each of these triangular subelements, you can get the 3 vertices to sit on the sphere, and you can, if you like, fold these basis elements so they sit nicely on the sphere. And when you do that, you get this wonderful dual de Rham complex. So I've illustrated it here with the sort of hexagonal primal grid and the triangular dual grid. So let me talk you through this just a little bit, keeping an eye on the time. So the bottom part of this diagram is just the de Rham complex that we saw earlier. So we have a vorticity space, which is kind of piecewise linear. We take a grad perp of anything there, and we get something in the velocity space. We take the div, we get something in the piecewise constant height space or geopotential space. But now I've illustrated with the hexagonal versions of the basis elements. But now we have a dual de Rham complex running in the opposite direction that lives on the triangular dual grid. So we've got piecewise linear functions that live on the triangular elements. Let's see, we have so-called Nadelec elements, again, for those in the know, where here we have a constant tangential velocity component along the middle edge. You probably can't quite make out the arrows there. You have a constant tangential velocity component and a constant curl, constant curl of that vector in the elements either side. And then you take the curl of that and you get a piecewise constant compound triangular element. And these two de Rham complexes are duals of each other, and they map back and forth between each other in a very nice and natural way. So the number of degrees of freedom in this V0 space and this V2 space is the same. So these are the vertices of the triangular grid, which coincide with the cell centers of the hexagonal grid. So there's the same number of degrees of freedom, and there's a nice map that you can construct in the usual finite element way of integrating by parts. You construct a nice reversible map between these two spaces. You can also do the same in the mapping between the two velocity spaces and the same between the two vorticity spaces. And there's some nice commuting diagrams embedded within this picture. So we can start with a field up here in the top right, and we can either take its gradient and then map to the primal grid, or we can map to the primal grid and then take its gradient. Either way, we end up with the same answer. And there's another diagram on the left half, another commuting diagram in the left half. Also, the one that we really wanted, or well, I wanted to be able to get my potential vorticity living in this piecewise constant space, because I can then reinterpret the finite elements as finite volumes and hit it with a finite volume advection scheme. So I need to be able to map my divergence to this space. And again, that comes out of the framework. So I can, let's see, what do I want to do? I want to start with a velocity down here, usual primal edge velocity. I can take its divergence and then map it to the dual vorticity space. Or I can compute the Coriolis terms, the V perps, map those to the dual grid, and then take the div and end up in the same space with the same answer. So again, that's the commuting diagram that we saw earlier, but now from the compatible finite element point of view. Okay, so some very beautiful mathematics behind that. But does it work? Well, yes, we implemented that again in a shallow water model. In fact, it was remarkable how little the code needed to be changed between the finite difference, finite volume model I talked about earlier and the finite element scheme. Just some mass matrices come into play, but apart from that, the code was remarkably similar, and a lot of it could be recycled. Because everything's now numerically consistent, we don't have that convergence problem with the Coriolis terms that we had previously. These figures don't really tell you anything other than to show you that a particular test case actually runs and gives us a nice potential vorticity field. So what was next? All right. Okay. So these wonderful compound compatible finite elements actually worked in shallow water. Sadly, it turns out there are a couple of practical reasons why they don't really extend into 3 dimensions. So I think I'll skip the reasons, but let me just say that's sort of where the story ends. We decided not to take the idea forward within the Gung Ho project. So that's where the compatible finite element story ends. Well, so that's where the compound version ends. We are actually using compatible finite elements in the Gung Ho project, but not these fancy compound ones, and we're on a cube sphere rather than hexagons. Okay, so for the final couple of minutes, I'm going to switch tack and talk about a vertical discretization problem. I think it was Nigel Wood who christened it the trilemma of the moist Charney-Phillips grid. So of course, the first few UCLA GCMs were based on the Lorentz grid, where we store the potential temperature at the same levels as the density. But later, Arakawa became convinced that the Charney-Phillips grid was superior because first of all, it avoids a computational mode, a mode of spurious hydrostatic balance. It can be excited and can do various types of damage. But also the wave propagation, and any waves that are dominated by buoyancy are captured more accurately on the Charney-Phillips grid than on the Lorentz grid. And indeed, some centers around the world, including the Met Office, have always gone with the Charney-Phillips grid rather than Lorentz, although I think they're probably in the minority. Okay, so what is the trilemma? Well, by definition, we want to, on a Charney-Phillips grid, we want to store the buoyancy variable, in this case, potential temperature theta, at the same place as W to capture the strong coupling between theta and W in buoyancy-dominated waves. So we want theta with W. If we're bringing moisture into play, then we want to store the specific humidity at the same place as theta to capture the coupling between temperature and moisture. It's a two-way coupling because latent heating and saturation specific humidity. So it's a two-way thing. But we also want to conserve the moisture in our models, which suggests that we want to locate specific humidity with density. And it doesn't take very long to convince yourself that we can't have all three of these things at the same time. So how do we get out of that? This is a nice piece of work by Tom Bendel and colleagues, just somewhere in the publication pipeline, not quite accepted yet. They realized that, again, we can exploit a similar sort of commuting diagram idea, but now it's in the vertical. So what we have to do, and I might flick back here, is construct a dual mass budget that lives at the W theta Q levels. So we construct some sort of averaged row and some sort of averaged or interpolated fluxes that satisfy an average mass budget, which we can then combine with the Q equation to get a water budget at the Q W theta levels. So I think that's the gist of it. So we have some mass fluxes that live at their usual places. We take their divergence for the usual density equation. And then when we average that to the W levels, we'll get a kind of averaged mass flux. We want to get the same answer as if we averaged or interpolated the mass fluxes, shifted them in the vertical, and then took their divergence. And if we can do that, if we can get this commuting diagram working in the vertical, then we'll have a dual mass budget that we can combine with the moisture equation to get a working moisture budget. And indeed, we can set things up so that we get not just conservation, but also consistency. So that if the specific humidity is constant, then it stays constant under the transport step. Of course, we shouldn't be surprised that this idea was anticipated by Arakawa in a couple of papers. I think this is where they applied a similar idea to the theta budget, and then Kono and Arakawa applied it to the moisture budget in an isentropic coordinate model. They weren't quite as general as Tom Bendel. They restricted their interpolation weights to 1/2 and 1/2, but they had the gist of the idea. This commuting diagram was already there in their work. Okay, so I think I've pretty well come to the end of what I wanted to say. So just to summarize then, this idea of a dual mass budget is actually present in a lot of Arakawa's work. If you look at what he wrote. He perhaps didn't make a big deal of it because it was just one piece of a more complex jigsaw, so he didn't pick it out as a particularly important idea, but it's there in a number of his papers, and it turns out to be key to a lot of what came subsequently as well. So if you want to have steady geostrophic modes on hexagonal sea grids or arbitrary polygonal sea grids, you need to use this idea. If you want to obtain accurate Rossby wave propagation, you need to take the divergence of the Coriolis terms and express those as something involving a dual grid divergence and a beta term. If you want to get accurate potential vorticity or potential entropy behavior for the vector invariant equations, in fact, the idea works on lat-lon grids as well. You recover some of the schemes that Arakawa and Lam looked at if you apply this idea on a lat-lon grid. But I've talked today about applying it on unstructured sea grids. All of that's to do with horizontal discretization, but it also pops up in vertical discretization if you want to get a consistent and conservative water budget on the Charney-Phillips grid, so as you can resolve the trilemma. And it also comes out in these compatible finite elements as well. It just comes straight out of the machinery that you get this commuting diagram and the dual mass budget. So I think I've come to the end of what I wanted to say. Yeah, there's just references next. If the logistics permit, I'm very happy to try and answer any questions you might have. But that's the end of my talk. Thank you for listening.
So we have time for questions, and I want to start with a really general one. That'll be occurring. My question is, are we there yet? What I mean by that is, can you see this work converging in some sense to an optimal dynamical core? Is there such a thing as an optimal dynamical core, and how will we know we're there?
Oh, that's an excellent question. I suspect there isn't a single optimal dynamical core. So I've been talking about my own favorite desirable properties. But if you go and talk to other model developers, they will emphasize other aspects. I haven't talked about computational efficiency at all and scalability. That's another consideration. Yes, you can get into a debate about, do you want to conserve potential entropy and then parameterize its dissipation, because ultimately you have to dissipate it, or do you want to build a potential entropy dissipating scheme from scratch? Again, one of the strands that Arakawa also looked at. Yeah, so I think the short answer is that you'll get different answers talking, if you ask that question to different people, and perhaps the gene pool, the diversity of possible models is becoming more diverse rather than converging, is the impression I get. But hopefully we are at least all moving forwards.
Hello, John, can you hear me, or do I need the mic?
Yeah, I think I can hear you. I just about make you out.
Is that any better?
Yeah.
I'll just speak up best I can. You talked about potential energy and potential entropy conservation, great, but I know that you've also done work on entropy conserving schemes, and I just wanted to ask you a more philosophical question along the lines of Dave's question. How important do you think that is when we're dealing with sort of real world fluids like the atmosphere? And is that a secondary consideration, or should we be paying more attention to that?
I think we should be paying more attention to it. So at the very least, I've noticed that I might give a long answer to this question. In a model that conserves entropy, will do a better job of conserving energy as well as a byproduct. So in other words, you make energy errors by not conserving entropy. On the other hand, of course, I think what's behind your question is that real world processes generate entropy. They don't conserve it. But I think the numerical errors we're making are probably bigger than the true sources, or at least they're in different places to the true sources. Yes, yes, certainly we should pay more attention to entropy conservation. But I might just add a little point to something I made, to a point I made earlier. So I was emphasizing the conservation of water with this. Can you see my slides sliding? When talking about the trilemma, I was emphasizing the conservation of water, but we can use this same commuting diagram to get conservation of entropy, because entropy lives at the W levels as well. But there's a little gotcha to watch out for, because if we use the flux form equation for predicting theta, there's some implied averaging there, and we actually lose the optimal wave propagation that we were using the Charney-Phillips grid in order to get. Now, there is a way out of that. You have to sort of tweak the horizontal fluxes to make up for the averaging of the vertical fluxes. But it's not quite a trivial thing. We actually lose something by working with the flux form equation for theta. I'm not sure. Did I answer all of your question, or did I miss a bit?
Yes, thank you. It was good to go.
John, thanks. I was glad to see moist processes brought in at the end, but I was wondering if you could spend a moment thinking about, all these elegant formulations tend to be first targeted at classical moisture not included processes, and yet for climate models, the moist processes and the way you carry around tracers, whether liquid or other, is extremely important to the behavior. And you get very weird looking, say, vertical structures of even temperature in some schemes interacting with moist convection. Is there a way to convince this community to turn their attention, or perhaps somebody's doing it that's aware of, to elegant or better formulations, canonical tests you have to pass with respect to interaction with, say, moist convection?
Okay, so I think I caught your question. Thank you. Yes, another excellent debating point. So I think there are initiatives out there encouraging exactly the sort of thing you mentioned. So there's a regular series of meetings initiated by Marcus Gross and colleagues on physics dynamics coupling, which cover a huge, broad range of topics, and encouraging folks to think more deeply about those sorts of questions. I think there are folks, I'm thinking of Christiana Jablanowski and colleagues who have proposed test cases that will go beyond the dry dynamical core and bring in moist processes. And we're all encouraged to try these at an earlier stage of model development and not get a perfect dry dynamical core working before we think about the physics. So I think there are people out there already promoting those things, and I agree, I'm all in favor of that. Yeah, do you think there is more we should be doing?
Of course he does.
That's why you brought it up.
Hello, John. This is Jim McWilliams.
Oh, hi.
Let me illustrate your remark about the diversity of views for dynamical cores. Your emphasis is on the conservation properties. I would argue that actually more consequent to the skill of a dynamical core is the way that it handles advection for complex flows, and in particular, what it does with its discretization error, the extent to which it is optimally diffusive and dissipative, which of course has a very large literature substantially inherited from the shockwave community. Comment?
I would not argue with that at all. So I didn't say much about it today, but can I scroll back? To the key point. There we yeah, so when I was talking about this TRSK approach, I hinted that my own preference was not to focus on, or at least my subsequent work was not to focus on conserving either energy or potential entropy, but to construct the potential vorticity fluxes so as to get an accurate advection of potential vorticity, and hope that the conservation properties would behave well as a byproduct of that. Yeah, no, I wouldn't argue with advection being incredibly important, especially for well, quantities with a long Lagrangian timescale. You've got to advect them with sufficient accuracy, and particularly areas like the tropical upper troposphere. I know the metaphys have found that some of the largest errors occur there and are very sensitive. Well, not large. The errors in the tropical upper troposphere, tropical tropopause region, are sensitive to the vertical advection scheme. And what seems to be happening is that air is just advected back and forth as waves propagate through, and it's ascending incredibly slowly. So the fields get dominated by the advection errors of this back and forth sloshing, and the errors can be reduced by designing the advection scheme to be more reversible, if that makes sense. So that was one of the ways they found to reduce a certain systematic biases near the tropical tropopause, precisely because the Lagrangian timescale is very long there.
That particular error might be reduced by using a theta coordinate. The one you
That
just
as well,
described.
yes.
Yeah.
Yeah.
Let me ask one more question and then we'll let you go, unless I see another hand. You didn't say anything about sound waves. So what do we do about sound waves?
Question. So I'm trying to think of a case where sound waves are actually intrinsically important, as opposed to the terms representing sound waves being important. I have seen a paper recently about wildfires, and they claim that the compressible equations behave differently from anelastic equations. But apart from that, I think we'd be happy if the sound waves would go away. If we could solve the soundproof system of equations as well as we could solve the fully compressible equations, we'd be quite happy with that, I think. So my default answer would be as long as the sound waves are not misbehaving, we don't mind too much. Would you agree?
Well, it'd be nice to get rid of them altogether instead of